So in the next 15 minutes, I will introduce you to one of the big projects we have in the EcoVision lab on global canopy height mapping with deep learning. So the main motivation is that there's a lot of forests being destroyed. So 178 million hectares forest lost since 1990, so which is approximately the size of France, Italy, Germany, and Spain together. And in 2019 alone, we lost 970,000 hectares in Brazil alone, and we see a rapid increase for 2020. And so our idea is that we combine the predictive power of deep learning and the global coverage of remote sensing to map a whole bunch of forest parameters like canopy height, biomass, and its change over time in near real time at global scale. And so how is this done today? So I've structured my talk into two different parts. The first one is this remote sensing using satellite imagery, and the second one will be using a space-borne laser scanner. So how is this forest inventories, how is this mainly done today? So it's either done manually in situ, so people go into the forests, they map an estimated biomass at certain measurement points, or another strategy is that there's airborne laser scanning, so laser scanners mounted on airplanes that are flown above the forests, and then you get 3D point clouds, and then you derive certain forest structure parameters. And the problem of both approaches is that it's hard to scale them globally. So to get all these measurements at global scale, it's super hard to achieve, very expensive. And if you think about repeating these measurements, let's say once every week or every month, it's basically impossible. You cannot send out thousands, hundreds of thousands of people all the time into the forests. So, and the idea is that we use the existing measurements, so reference data that has been collected already, to train a deep learning engine using satellite imagery to predict canopy height. And those of you who have worked with remote sensing data and satellite imagery already know that a lot of the vegetation signal is recorded in different spectral bands of the satellite. So Sentinel-2, this European Space Agency satellite, has 13 different spectral bands recording the reflectance of the sunlight of the vegetation in different channels. And another hint that hints at particular properties of vegetation is in the context, so the spatial context, so particular texture in the image. And we basically treat those two sources of evidence, so the spectral signature of a particular variable, as well as the spatial context, so the texture and the image separately. So we use this approach from Cholet, CVPR 2017 paper, and we do separate convolutions. So we have a separate convolutions in the spatial domain. We first filter in the spatial domain in our deep network, and then we filter the output of that in the spectral. And then we convolve across the spectral bands. And then there's something else. So if you come from computer vision, you say, okay, just use the best computer vision deep learning network, what Deep Lab V3 or whatever you want to use for semantic segmentation, apply it directly. And I can tell you this does not work. So if you working with this medium resolution satellite imagery, so each pixel of this image is a 10 by 10 meter pixel on the ground. If you want to tell anything about trees, then these objects are smaller than a pixel. So what you would want to do is you really want to avoid any down or up and any down or up sampling. So you get rid of this bottleneck architectures, and you have stride one. You avoid any kind of max pooling that results in spatial downsampling. And then basically you have a rather compact deep network. In our case with 18 identical separate convolutional blocks that we see here. And they do not only learn spectral features, but they also learn the spatial context in the images. And the pipeline and overview is here. So the input really is this raw Sentinel-2 image, or when I mean raw, I mean the atmospheric corrected image. And then we do basically pass it through this deep learning architecture, and the output is directly a canopy height per pixel. So each 10 meters we have one canopy height, and the canopy height is color encoded here. So the more orangey, the higher; the more dark and blackish, the lower. So, and then I was asked before that I should add some mathematical equations here to make this look more, this talk look more serious. So here's one of them, although it's a simple one. So that's also something, it's a regression task, of course, because we're predicting a continuous variable vegetation or canopy height. So we use a Euclidean loss function. And then we add an L2 penalty term for the model parameters as a regularizer here. And what this basically does is when we train this model, so this is the entire loss function. The regularizer is here in pink, and unlight in green is the Euclidean loss. And what we have here is yi is the ground truth. So it's a canopy height at a certain pixel location. And then we have the pixel intensities as observations. And we're looking for this function that maps this pixel intensities to vegetation height predictions. And then this is the regularizer that I just introduced. Yeah, and you know, and with the supervised machine learning, we have to look for reference data. And those are the two countries where we could get our hands on good reference data. So one is the country most of us are based in. So this is Switzerland. And for Switzerland, we have a good canopy height map for the whole country, which is kind of up to date and basically maintained by WSL, Forest Research, part of ETH also. And a second part is contributed by NASA colleagues. This is results from the NASA Elvis campaign. So this is the country of, or part of the country of Gabon in West Africa. And the specialty here is that they have a lot of very high trees and a lot of protected nature, so very intact, dense native rainforests here. And this has all been flown with a full waveform LiDAR, airborne LiDAR, so very beautiful data as reference data. So if we apply, so we train our model always on part of the data, then validate and test. And if we do 5-fold cross-validation, then we come up with these results for the test data set. So these are two plots, one for Gabon, one for Switzerland here. And for Gabon, we have trees between 0 and 60 meters high, even a bit higher. And we come up with a mean absolute error of 4.3 meters. So mean absolute error, for those who are not familiar with it, you can basically say, okay, plus minus, the accuracy is plus minus 4.3 meters roughly. For Switzerland, we are better. So mean absolute error of 1.7 meters, but this is not surprising because the top heights of the trees are much lower, so up to 40 meters, 35 meters. And of course, we have also a bit more, let's say, ground pixels in there that have almost no canopy height. And what we want to see, the most important thing is that if we have the ground truth here on the x-axis and the predictions on the y-axis, we want the predictions to lie on the diagonal, which says, okay, we're predicting something reasonable here. There's a strong correlation. And if we then split the error that we do into the different canopy intervals, so we have the green color for Gabon, blue for Switzerland, and we now look, okay, what's the error in the interval 0 to 10 meters, 10 to 20 meters, 20 to 30? We can see that when we go further here up in Gabon, above 60 meters, there's not much we can learn with our model. So the signal that we get from the canopy top is saturating, and we make very large errors. So errors up to plus minus 60 meters for trees above 60 meters. So, and something interesting that we also found is that the Swiss ground truth actually had a lot of outliers and gross errors. And this is being corrected now, especially at the very steep slopes in the Alps, because the ground truth was generated by combining a digital surface model with the underlying digital elevation model. So if there's a slight shift, then at the steep slopes, we get these misalignments, and then suddenly people think we have 50-meter high trees at the steepest slopes, super high in the Alps, which is of course not true. So this is being corrected now. Yes, and then we compare with freely publicly available data sets from NASA here for the country of Gabon. Again, the color is encoding height. So very bright orangey stuff is very high. So up to 60 meters, well, dark is close to 0. The NASA model, which is an older one here from 2011, had a special resolution of 1 kilometer. So ours has a 10-meter resolution. And we are zooming in into this white box here, which is an interesting mangrove area, this delta here. And we see that when we move over to our model, that we nicely can map all these very high mangrove trees. So up to almost 60 meters high mangrove trees. And a lot of very fine-grained details in the country, which might be helpful for a lot of further processing for the environmental sciences. The comparison in Switzerland is even more interesting in this case, because the model here, the old NASA model, is completely wrong, basically, for Switzerland. It tells that there's 40-meter high trees basically everywhere, which is an error due to a lot of radar processing in steep slopes. And ours is much better here. So if we zoom in here somewhere in Graubünden in the white box, you see that there are only super high trees at 1 kilometer resolution, and ours just really has a nice result of this very fine-grained detail for trees up to above 30 meters height. So when we want to scale this and not only compute for Switzerland, which is a beautiful but small country, and we want to go global, we have to look for other reference data. And this is when we teamed up with the NASA JEDAM team, with Ralph Dubai and John Armston, Ralph is leading the NASA JEDAM effort, which is they put a full waveform scanner on laser scanner on the International Space Station, which circles the Earth, takes a lot of measurements, and we are then calibrating this data, and based on these sparse points, we then learn our model, use the central two image, and make a dense canopy and biomass map globally. So this is how it looks. This is the ISS, and we can now see here the laser scanners mounted on the ISS. This is a payload here, and it has 8 different beams that look down on Earth and scanning the Earth in a sparse grid. So, or sparse distribution. So the swath is a bit more than 4 kilometers, and you see there's big gaps between those different tracks. And each pulse that is sent out records a lot of reflections, so more than 1,000 reflections. And this is basically then measuring the whole structure of the forest. So you see here the intensities to the right, and each pulse is then basically, each distance is encoding the height. So there's a top peak and intensity, the canopy top. Then there's further structures down here where there's reflections in the branches in the trees, and then there's a bigger peak at the ground return again. And we basically now aim to predict the canopy height from this raw full waveform by just measuring the distance between this top peak here and the ground peak. And this is actually harder than one thinks. So there are mechanistic models out there that do that. But we are basically taking out the deep learning bazooka here and training an Bayesian deep learning approach. So this is such a raw full waveform that we look at this canopy top and ground here again. And what we do is we have a CNN, a one-dimensional one, so convolutions that basically learns given reference data that the NASA colleagues Ralph and John also provided us. We learn a model to predict from raw input full waveforms directly the canopy height. And we do this with an ensemble of models, and each CNN model is then trained separately, starting from a random initialization. We have 2 outputs per model to approximate the conditional distribution, so the mean and the variance. And then we minimize the Gaussian negative log likelihood. And we use stochastic gradient descent, which is a standard approach. And the interesting thing then is that we do not only get very good predictions, like deep nets usually do, but we get very well calibrated uncertainties that we can later use for filtering. So we really know when we make a prediction for a vegetation height, a canopy height, how much can we trust it. Yeah? And we can get rid of those predictions that are just where the model is just not confident that it made a good prediction. And so to combine these 10 different outputs here, we do ensemble averaging. So basically we follow this approach that is also introduced or was commonly used in computer vision, that we basically estimate the model uncertainty, so epistemic uncertainty, aleatoric data uncertainty. And we combine all of those different measurements from the different models, basically by fitting a sort of implicitly a Gaussian through all of this, and then estimating the variance. And this is what we can then assign to also any new application in the test run. And I'm almost at the end already of my talk. This is just two results now. So this is a global map of this JEDI footprint. So remember that it's a sparse, yeah, so it's not a dense map. And it only goes up to where the ISS wheel flies. So here to the Canadian border and to northern Germany. And you can see that, yeah, we nicely get the structure here. We get the root mean square error of 2.7 meters globally. So this has to be treated with care, of course, because there's a lot of, so there's also very low measurements. And this is already after we do a filtering. So we throw away the 30% most uncertain measurements, which is something we can do, an advantage of a Bayesian deep learning approach. This is then a map of the uncertainties. So colors encoding the uncertainty here. So the more yellow, the less certain, so the more uncertain. And you can see that it mostly correlates with the height of the trees. So the higher the trees, the bigger the uncertainty. All right, so that's it for now. So of course, all of this is thanks to a great team, and particularly this guy. So this is Nico Lang, who did all this work that I just presented. I'm running around presenting and trying to get funding, but those people who are really doing the work are here in the photo. And for this talk, this is Nico. So in general, I think anything in environmental sciences and this combination with deep nets is very interesting because it's a different problem setting than what we usually have in machine learning or computer vision. So you cannot just go and say, look, I just download 1 million images from the web and then give it to 1 million people or less on Amazon Mechanical Turk and label more data. And if I don't have enough data for training, I just label more data. In our case, it's impossible. Yeah. So we cannot send out thousands of people into the forest to measure biomass or something. We have to live with a lot less training data and also a lot less accurate labels. So the reference data is less accurate usually too, so there's much more label noise, which leads us to the conclusion we need to basically really on a technical level develop new machine learning methods that are a bit off mainstream, I would say, to solve these problems, which is something that my group is doing. And in this sense, something very interesting from my point of view is combining machine learning with physics-based modeling, so the expert knowledge that we have out there. For example, in hydrology, where we have Navier-Stokes equations, combine them with the deep nets to get the best of both worlds. And something that is interesting in the environmental sciences in particular is that we very often have to depart from the grid, like the image-based deep nets, which are well understood, to basically arbitrarily distributed sampling, which then speaks for geometric deep learning, so graph convolution, neural networks, and so on, which is something that we're exploring in my team. And if you guys listening are interested in collaborating, please feel free to reach out. We are happy to discuss. So thanks a lot for listening, and happy to answer questions.